Hello, this is Mr. Delamorte here to talk about topic 6.12, integration with partial fractions. So this will be our third technique of integration. We know U substitution, we know integration by parts, and we know partial fractions. Now, partial fractions is a method used, it's a way in which we can deconstruct a rational function where the denominator is factorable. So just something you might be familiar with. If you have two fractions, two rational functions, and we add them or subtract them, we can get common denominators, as you can see in this blue box. And then as soon as we get common denominators, then we can combine it into one fraction, distribute, combine our like terms, and get our rational function. Well, what if I want to go backwards, though? What if I start with the rational function? I want to deconstruct it. I want to break it up into two smaller fractions, and then I want to integrate those smaller fractions. Most of the time, we will get natural logs, but we're going to go through this, and we're going to kind of show, how we can deconstruct it into these two smaller components. So I have a couple examples as well as a few practice that we're going to go through. So I want you to see, one, always keep in mind the original problem, okay? And what we're going to do is, I'm going to use my red pen here. I'm going to factor the denominator. So I'm going to have a 1 over x plus 2, x minus 1, dx, okay? Then, if I do a partial fractions, if I deconstruct this, I want one of my denominators to have one of the factors from the denominator, and I want the other fraction to have the other denominator. Okay, now I don't know what goes in the numerator, all right? It can't just be ones, all right? That's the hard part. So what I'm going to do is I'm going to make them an A, and I'm going to make them a B. And I'm going to add these together. All right. Now, seems backwards, but with A and B, what I'm going to do is I'm going to get common denominators. So I'm going to say A over x plus 2. And I'm going to multiply this by an x minus 1 plus B over x minus 1. And then I'm going to multiply it by an x plus 2. Now, if I distribute out the top, I have an ax minus a all over x plus 2, x minus 1, plus a bx plus 2b all over x plus 2, x minus 1. Now, I'm going to kind of go through the steps here. If I combine these into two fractions, I'm going to put like terms together, ax plus bx. And then I have a negative a and a positive 2b all over x plus 2, x minus 1. Now, to go a step further, I'm going to take an x out of the first couple terms. I know a plus b times x minus a plus 2b all over x plus 2, x minus 1. Now, I want you to look back at the original problem, okay? This original problem, I'm going to write it in kind of a slightly different way, is the same thing as saying 0x plus 1 all over x plus 2, x minus 1. Now, if you notice, I put in a 0x. Why did I do that? Because I didn't have any x's in the numerator. So if you take a look at this fraction, I have a plus bx. Well, I know a plus b has to be 0, because if I add these together and I want it to be equivalent to my original problem, I don't want there to be any x's. So I want the a and the b, if I add it together, to be 0. Furthermore, I want the negative a plus 2b is going to end up being a positive 1 because these are my constants. Okay, and actually I should box that negative 1 in there with it. Those are my constants, and if you notice, I have my constant here. Okay, so the a plus b gave me the coefficient of 0, and the negative a plus 2b gave me the constant. So now I'm going to do a little elimination. If I add these together, those cancel. I get a 3b equals 1, or in this case, b equals 1/3. So now I can plug this back in to any of the equations. So I'll do a plus my b, which is 1/3, equals 0. So I know a has to equal a negative 1/3. And I'm going to rewrite this problem as a, which was a negative 1/3 over x plus 2, plus b, which was a positive 1/3 over x minus 1 dx. Now, I can integrate these separately. I'm going to pull the negative 1/3 out. Okay, and if I integrate 1 over x plus 2, that's just going to be the natural log of x plus 2 plus 1/3 the natural log of x minus 1 plus c. And now properties of logs say that I can write this as the natural log of x minus 1 over x plus 2 to the 1/3 power. Let's see. This would be my final answer. So at the end here, you might have be a little less familiar with some properties of logs. Remember, if you have two logs that are being added together, then we multiply them. If we have two logs that are being subtracted, we divide them. Any coefficients can become exponents. So in this case, I had a negative. So I kind of treated it as the second term, this natural log, the x minus 1, was being subtracted. And I'm going to subtract off the first term because it was negative. So that's why I put it on the denominator. And then it was all to the 1/3 because each of those had a 1/3 coefficient. Now, if they had different coefficients, then I would raise the numerator and denominator to different exponents. Okay? So I'm going to do example 2. It's similar, but it requires one additional step, and then we'll kind of go through it. If you notice, the numerator has a higher degree than the denominator. Now, I do want to kind of mention I have a 2x cubed minus 4x squared minus 15x plus 5 all over, and I can factor this to an x minus 4x plus 2, right? So I can factor this, but the problem is the numerator is just too big, okay? So I want to synthetically divide it, or in this case, I'm going to long divide it. So off to the side here, I'm going to put the numerator inside my division, 2x cubed minus 4x squared minus 15x plus 5. And then on the outside, I have an x squared minus 2x minus 8. So now if I long divide this, I would have to multiply it by an x, 2x. That would give me a 2x cubed minus 4x squared minus 16x. If I subtract, well, that's convenient. I get a 1x plus 5, and that would be a remainder, right? So this problem is equivalent to 2x plus my remainder, 1x plus 5, over that same denominator. Right? So now I'm going to do a partial fractions on that remainder. I know a over x minus 4 plus b over x plus 2. So I'm going to say a times x plus 2, x minus 4, x plus 2, plus b over, wow, this is going to get multiplied by an x minus 4. All right, I'm going to distribute. I have an ax plus 2a plus bx minus 4b all over x minus 4 x plus 2. Okay, now if you look at the terms that have my x's in them, right, I have a positive a and a positive b. I know a plus b has to be 1. Furthermore, I know that 2a minus 4b has to be my constant in the original problem of 5. All right, so now I can do a little elimination. 2a plus 2b equals 2. Let's make that negative. Multiply everything in that first equation by a negative 2. Leave the bottom equation the same way. If I add straight down, I get a negative 6b equals 3, which means b equals a negative 1/2. Now, if a plus b is 1, that means a has to be, let's see here, let's double check something. A minus 1/2 equals 1. If I add 1/2, I'll get 3 over 2. So a is going to be a 3 over 2. So if I write this integral, I can now say I have a 2x plus my a, which is 3 over 2, over the x minus 4, plus my b, well, in this case, it'll be minus my b. Well, we'll just keep it a plus, that's fine. A negative 1/2 over x plus 2 dx. So now I can integrate each of these terms, which the antiderivative of 2x is just x squared, plus 3/2 the natural log of x minus 4 minus 1/2 the natural log of x plus 2. And if I do this, I can combine those logs together, which would give me a natural log of x minus 4 to the 3/2 over x plus 2 to the 1/2 plus c. And that would be my answer. Okay. So please feel free to rewind, email. If you look further on this packet, I have more examples here, and I'm going to write out some worked out solutions to them, so that way you'll be able to check, but there are some questions there for you to look at. Again, I want you to take a look at this. The first example I had, I could just factor the denominator. I did a partial fractions deconstruction, found my a and b, and then integrated both of those fractions. For number 2, the denominator was still factorable, but the numerator had a larger degree. So I had to do a little division first. Then I had to do a partial fractions on the remainder and then go from there. Okay, so I'll do these examples so that you can see it. There's 6 of them. Check out that work, and then hopefully you can do the third method of integration.